Hi there, Mrs. Thompson here, and today we are talking about the ideal gas law. The ideal gas law actually combines a few gas laws into one, and that is the combined gas law, which is already a mixture of Charles' law, Boyle's law, and Gay-Lussac's law, and Avogadro's law. And so with the combined gas law, if we look at it, it looks like this: P1V1 over T1 equals P2V2 over T2. Remember that these are in two different conditions with the same gas. Okay, if we just cover up one side and we look at it for one condition, all of this would be equal to a constant, which we call K. Okay, now Avogadro's law states that the number of moles of gas, which is N here, is directly related to the volume of the gas. So the more particles you have in a container, the more volume it will take up, as long as that container is flexible. Okay. We can rewrite this to solve for the constant, which is K, and it would look like this: volume over N is equal to K. Now if we combine those two, we have PV over T equals K, and then we throw in Avogadro's law, which says that N would be underneath V, so we just put it right next to it, and that's equal to K. Then we could rewrite this to make the ideal gas law, which is PV equals nRT, which is close to what I have here over here on the left, except for we have R, which is our constant. This constant gets a new letter. It's the letter R, which we call the ideal gas law constant. Okay, something that this ideal gas law that allows you to calculate that the combined gas law does not is the number of moles of a substance. It also lets you look at a gas at one set of conditions, not a bunch of conditions, or excuse me, not two different conditions, just one set of conditions. All right, so the variables that you need to know are P, pressure, and when we're doing these, which is different from the combined gas law, we have a specific set of units that we have to use. That's because of our R value. All right, so for pressure, you have to put them in atmospheres. For temperature, in Kelvin. For volume, in liters, not milliliters. And N is in terms of moles. And then R is what we call the ideal gas constant. Its value is up here. It's 0.0821 atmospheres times liters over mole times Kelvin. These little dots are just multiplying. Okay, so how did we get this R? R is actually calculated, and it's calculated using ideal conditions. And in those ideal conditions, we use 1 mole of that gas, and then we keep that gas at STP, standard temperature and pressure, which is 1 atmosphere of pressure and 0 degrees Celsius. And we find the volume of 1 mole of gas at that standard temperature and pressure, and it's 22.4 liters, and then we calculate what R would be, and we get the 0.0821 that I was telling you earlier. There are actually other values for R available, and they have different units. The reason why they're different is because they use different units of pressure. Remember, there are a lot of units of pressure. And you can go through and you can pick whichever R value you need based on the units you have. For our purposes, what you will get on the test is an R value in terms of atmospheres. So we'll always use the 0.0821. So we'll always convert to ATMs. Before we start using the ideal gas law equation, we're going to quickly talk about real gases versus ideal gases. Now, an ideal gas is one that follows all of the postulates of the kinetic molecular theory. In particular, those particles do not take up any space, and there are no intermolecular attractive forces between those particles. Now, in the real world, no gas is truly ideal. Under the right conditions of temperature and pressure, you start to see some deviations. And so, when we're talking about pressure, if we have a really high pressure, okay, the amount of space that it takes up becomes significant. So here, compared to, this is the volume of the gas compared to the entire space of the container that it's in. It's negligible, it's small. But over here, it's relatively significant because it takes a good amount of space up. Okay, so in high pressure, this happens. The intermolecular forces can also be felt in a gas. And so when the intermolecular forces are felt in a gas, they no longer travel in straight lines, they travel in curved paths. Okay, so you need to know when gases are going to deviate from ideal behavior. That is when pressure is high, they're squished together, and temperature is low, they're moving slowly. When this happens, they start to feel those intermolecular forces, and they come closer together. Okay, then their volume becomes significant. So here's this graph to show you the difference between a real gas and an ideal gas. Now we're going to stay within volumes and pressures here, so this difference isn't going to be enough for us to worry about. However, if you move on to take AP chemistry or chemistry in college, you may have to use the van der Waals equation, which helps you correct for a large amount of pressure and volume. All right, so here's our first problem. When you're doing these problems, you do have to write the given and the unknown and all the work. Okay, and so I want you to list your variables because it's going to become important when you have like 5 different gas laws and you don't know how to solve it. What you're going to have to do is list those givens and see which givens match which equation. All right, so we're dealing with PV equals nRT, which we just like to call PIV nerds. All right, so here's our problem. Find the volume of 85 grams of oxygen. So find the volume. That means volume is unknown. 85 grams of oxygen. Now, in PV equals nRT, what is grams? It's none of those. That would be mass. Instead, you might want to write this down. When you have grams of something, what you can do is you can always change grams into moles. Okay? If you know what the formula of that substance is, change those grams into moles. And that's exactly what we're going to do. So 85 grams of oxygen, we'll convert that. We know that 1 mole of oxygen is 32 grams, and so we get the N, which is moles, is 2.66 moles. Okay. Then it says 25.0 degrees Celsius. And so there's our temperature, right? Celsius is temp. We need to change that to Kelvin, so add 273.15, then round to sig figs. That's going to be 298.2. Okay. Then we have a pressure of 104.5 kPa. All right. Now, when I gave you the R value, I said you had to put these in certain units. Moles, which we've got. Kelvin, which, yeah, we did that. I forgot to tell you why, but it's just like the combined gas law equation, temperature has to be in Kelvin. All right. And then kPAs, well, that's not going to work. The units for pressure we need are atmospheres. So we'll convert that. You know how to do that. It should be simple. 1 atmosphere is 101.3 kPAs. Okay, that cancels. And I get that the pressure is 1.032 atmospheres. Great. So the given side is kind of lengthy because we got some conversions to do. Sometimes you have just, it'll tell you exactly what you need. And other times it'll be a little more complicated and you'll have to convert. Okay. What's missing? So I have V, N, T, and P. We just need R. I'm not going to write R with all its units. I'm just going to write R. We have it. Check mark. All right. So let's solve the problem. Now, just like with the combined gas law, I want you to write the equation down and rearrange it to solve for the variable that you need, which is volume. So don't just plug stuff in. All right, so I'm going to solve for volume, which means I need to divide both sides by what's being multiplied by volume, which is pressure. And so my equation just becomes volume is equal to N times R times T over P. All right, okay, so now we can just plug stuff into the equation that we have made. Okay. And I do need to write all of the units, especially the units for R now. All right, so just plugging all the information that I've gathered in the given side into the work side. And then plug it into my calculator and I get 63.1. Now we need to figure out what those units are. So let's get rid of all of the units that cancel, which is why you have to write the units for R. Moles are on top here and on the bottom in R, so those cancel. And then atmospheres are on top in R and on bottom in the bottom part of the equation. And then we also have Kelvin, which cancel. Okay. This leaves only liters left, which means my units are in liters, which makes sense because this is volume. We're finding the volume, so 63.1 liters. Okay, got one done. Now, we solved for volume, but I could have taken that equation and solved for N. I could have solved for T. I could have solved for P. I could take that equation and solve for any one of those variables. And so you're going to have to be able to rearrange that equation and solve for the variable that you need. Now, your algebra should be good enough to do that. If not, we can work on that in class. Okay. All right, so here we go. Here is a different version of the same equation, except for this version uses molar mass and density. And so it's just a rearranged form of Pivnert. Okay. So it says what's been substituted here is instead of moles, we have taken M over capital M, which is mass over molar mass. Okay, because that's how you find the number of moles. You take the mass, you divide it by the molar mass. It gives you the number of moles. All right, and so the reason why they use that is because that will allow us to manipulate the equation so that you have M over V. Okay, and so with M over V, that is another thing that we've done in the past. M over V is just density, mass over volume. So we get this new equation, Pivnert. PM equals dRT. And the reason why we like this equation is because we can use it to find the identity of a gas by looking at its molar mass. All right, so here's our example, Pivnert. What is the molar mass of a pure gas that has a density of 1.4 grams per liter at STP? All right, so what's given? So we want to know the molar mass. That's capital M, that's our question mark, that's our unknown. It has a density of 1.40 grams per liter. Now that's the unit for density that needs to be in grams per liter. STP. STP is standard temperature and pressure. So the pressure is 1 atmosphere. Throw in as many sig figs as I want. It's a set defined quantity. And then the temperature is 0 degrees Celsius or 273.15 Kelvin, which is what I need, so I'm going to put it in Kelvin. And then what else do we need? So we have M, D, P, and T. We need R. And remember, R we've got, it's in our back pocket, so I'm just going to put a check mark there. All right, so let's write our Pivnert equation, rearrange it to solve for what is the molar mass, so M. So if I do that, it would be M is equal to dRT over P. So hopefully you can do that, move that over pretty easily. So we'll just plug it in. There's our density, the value of R, and the temperature divided by the pressure. And if I plug that into my calculator, I get 31.4. That's 3 significant figures. Rounded to the least amount of number of sig figs. Then we need to figure out the units. Liters cancel. Atmospheres cancel. Kelvin cancels. So what's left? Well, we have grams and we have moles. But we have grams on top and moles on bottom. So this is grams per mole. 31.4 grams per mole. Which is great because guess what? That's a unit of molar mass. All right, so what if I asked you this question? Is this gas oxygen or fluorine? So you would look at the molar mass of oxygen and the molar mass of fluorine. Oxygen is 32 grams per mole. Fluorine's about 38 grams per mole. It's 19 times 2. It's closer to the molar mass of oxygen, so we're going to go ahead and say that this is oxygen. All right, well, that's it for today. Hope you found working with the ideal gas law equation pretty easy. Remember that there are many variations that we can use the same gas law. Another thing to remember is that if you're given grams, you can find moles, or if they ask you for grams, you can use moles and then change it into grams. Okay? Have a great day. I will see you tomorrow.